Betacam SP Symptoms Tape. Section 1. Mechanical System. Video head wear. This is an example of a good video head. Note the relatively flat shape and square corners of the RF waveform for both fields. On a good head, the RF amplitude is 1 volt peak to peak. Here we see an example of a bad video head. This is characterized by the loss or partial loss of the RF of one field. Note the flickering effect due to one field not being played back. Possible causes may be a dirty or damaged head, or an electrical problem affecting one channel. Eccentricity. Here we see the correct alignment of head drum eccentricity. The center axis of the upper drum is aligned with the center axis of the lower drum. Note that the corresponding playback picture in the upper right-hand corner is without defect. Now we see a misaligned upper drum. The center axis of upper drum has been purposely misaligned. Note the disrupted picture of color bars on the monitor screen. In the upper right-hand corner, we see the RF waveform. The dissimilar shapes of the two envelopes are often an important clue, suggesting an eccentricity problem or a damaged or clogged video head. Control track head position. This is a CTL head correctly adjusted. You see playback video without distortion. A symptom of CTL head position misadjustment is picture distortion noticeable at the top of the picture. CTL head position affects the phase of CTL signal, which is used to position the tape for optimal tracking by the video head. Placing the tracking knob out of the center detent position simulates CTL head misadjustment because it also affects the phase of the CTL signal. Entrance side tracking. Here the waveform shows tracking correctly adjusted. Note the flat top and the square corners of the RF waveform. The entrance side of tape path is controlled by the tension regulator arm and by tape guides 1 and 2. Note the distortion of the RF waveform. This is the result of incorrect adjustment of the entrance guide, which on the BVW-75 is the tension regulator arm. When doing the video tracking alignment, it is important to check for visible defects in the entire tape path, not just at the entrance guide. Tension regulator slantness. Here we see the unit set up with the proper tension regulator arm slantness. Note the sharp corners of the entrance side of the RF envelope. As we misadjust slantness, note the tapering of the entrance side of the RF envelope. A slantness problem is often not noticeable in the play mode. We need to shuttle back and forth in the DT mode in order to see the effects of a slight slantness problem. Also, look for the tape to ride up or down on the entrance side guides. Exit side tracking. Here we see the tape path is correctly adjusted at the entrance and exit sides. The zenith of the audio timecode assembly should be correctly adjusted before performing video tracking. Otherwise, this can negatively influence tape path adjustment. When we misadjust TG3, we see the effect at the exit side of the envelope. The corner rounds off, and if we continue to misadjust TG3, the envelope collapses and the picture is affected. Pinch roller. Here we see a worn pinch roller operating in the play mode. In normal play, a worn pinch roller is not always noticeable. However, when we shuttle the tape back and forth in the DT mode, the tape disturbance is apparent. The tape wrinkles as it rides up and down at TG4 and guide C as it is shuttled back and forth. In the upper right-hand corner, we see a drawing showing a good versus a worn pinch roller. Notice how wear can cause the pinch roller to become concave at the center. Here is a close-up of a worn and glazed pinch roller. Tape path tolerances are very small, and the concave shape of a worn pinch roller is not readily noticeable to the human eye. Real DME. Here we see the two real DMEs. DME stands for divided magnetic element. The DMEs are used to measure real table rotation to calculate real torque. If a DME is placed too far away from the real table, the real servo cannot correctly control real table rotation. This causes real servo problems and can also result in tape damage. Real torque. Here we see smooth transitions while changing tape direction. Note the stable tape path as tape is shuttled in both directions. As we misadjust RV13 on the SV83 board, we quickly lose tape stability. Note tape slack at the entrance side and the motion of the tape drawer arm attempting to compensate for tape slack. If tape slack becomes severe enough, the unit goes into auto off with an error 3 displayed on the counter. Cassette compartment. If the cassette compartment foot is not placed correctly in slot, the unit will go into auto off. An error code will be displayed. Error 20 is the cassette loading problem. This problem can also simulate a reel or a tape height problem. Error 1 through 4 are concerned with tape slack, tape spillage, and tape damage. It is even possible to bend the cassette compartment. If it is incorrectly inserted and the cassette compartment stay bar is tightened down. If this happens, the cassette compartment will probably have to be replaced. Section 2. Servo System. Reel FG. Proper reel motor operation is critical for proper tape tension and consistency of tape travel. The properly adjusted FG waveform has a 50% duty cycle. When we misadjust the FG duty cycle and put the unit into rewind, the unit goes into auto off with an error 2 displayed on the counter. Another symptom of a misadjusted reel FG duty cycle is a rewind speed considerably less than 24 times play speed. When we misadjust the FG duty cycle signal in play, the unit goes to auto off with an error 3. The error 3 indicates a tape tension of less than 15 grams. The first 5 error codes are concerned with real problems. Capstan acceleration. Here the capstan is correctly adjusted. Note the smooth, wrinkle-free tape path. RV8 on the SV84 board controls capstan acceleration. If this pod is misaligned, the symptom is tape slippage and tape jitter along the entire tape path when the tape transport modes are being changed. For example, from forward to reverse and reverse to forward. Tape jitter and wrinkling are most noticeable at the tension regulator arm and the tape drawer guide. The tape flow becomes stable once the capstan is locked in a particular mode. The capstan acceleration circuit adjusts for changing tape speeds, as in the search mode. If capstan acceleration control is too erratic, the machine will go into auto off and display an error 02. Here we see the effects of improper capstan acceleration control on the picture monitor. When the tension regulator arm jitters, the picture also jumps vertically. If RV8 is misadjusted and we shuttle tape back and forth in DT variable mode, picture breakup will be the result. This is because waveform excursions are exceeding the specification as listed in the service manual. Capstan free speed. When the capstan free speed is adjusted correctly, the tape runs smoothly and there are no observable problems. The servo lock light, located directly below the red record switch, is lit. The servo lock light is difficult to see in this tape. It is easier to see the light go off. It blinks on and off with occasional signal breakup and stays off with more extreme misadjustment. The symptoms of capstan misadjustment can be similar to a tracking problem. The Sony specification for servo lock on the units is equal to or less than 2 seconds in a play mode. When we switch from the record playback head to the DT head, and we misadjust the capstan free-speed control pot RV1 on the SV84 board, vertical jitter and loss of servo lock will result. Shuttling in the DT mode, with the unit still misadjusted, results in vertical jitter while the speed is changing, and the servo lock light remains off. Drum-free speed. With the drum-free speed control pot RV102 on the SV84 board, correctly adjusted vertical lock is steady and the servo lock light is lit. As drum-free speed is misadjusted, occasional vertical roll occurs and the servo light blinks. As misadjustment is increased, the vertical roll becomes severe and the servo light remains off. Eventually, the unit switches to auto off with an error 08. RF head switching. In order to see the symptom of an RF switching problem, a monitor with an underscan control is required. The switching problem, or glitch, appears at the bottom of the picture. Without the underscan capability, the glitch is not visible. RF switching becomes a problem when the switching point, usually occurring in the vertical interval, extends into the visible part of the picture. When correctly adjusted, the switching point occurs 2.25 H before vertical sync, out of the visible portion of the picture. Section 3. Dynamic Tracking Servo. DT disable. This is what DT should look like when it is correctly adjusted. As we shuttle back and forth between -1 to +2 times normal speed, there is no breakup and the picture is without noise. Next, we see what DT should not look like. As we shuttle back and forth, we see various picture faults. These problems could be caused by a number of things. That is, dirty, worn, or misaligned DT brushes, bad ribbon cable on the preamp board, slantness problem, mechanical defects, connector 661 loose or disconnected, or S201, bit 3 on the DT13 board is closed. DT tracking. Here again we see correctly adjusted DT. As long as we have a flat, stable envelope of sufficient amplitude, our picture is usually okay. The BVW-75 DT system is very forgiving. Notice how much disturbance of the RF envelope occurs before DT is noticeably affected. The picture disturbance is a result of improper tracking. DT brush noise. When the brushes become dirty or worn, we see a characteristic set of symptoms. The evenly spaced, bright, dash-like lines distributed evenly throughout the picture is indicative of a brush or slip ring problem. Brush noise problems often occur in a dusty environment. Memorizing this set of symptoms can be instrumental in bringing about a quick fix at some time in the future. Section 4. Video System. No chroma in composite mode. This is an example of a problem that exists in only one input select mode: loss of chroma in a composite mode. You can see that the front panel select switch is in the composite position when the problem exists. In component mode, we see a color picture. This gives us a clue that if a problem does not exist in component modes by the process of elimination, this leaves the DEC 27 board, since this board only processes the composite input signal. Going through a thorough operational check, including checking all the various input modes as well as all the functional modes, can quickly eliminate much of the machine as the possible problem. This can speed up the troubleshooting process. Multiple vector dots. Here we see a vector scope showing vectors of 75% color bars with multiple vector dots that are apparent while in a two-field capstan lock mode. No SCH phase correction circuits operational. The multiple vector dots represent residual subcarrier from the YC separation process of the input composite video signal. When we switch from 2 to 2/4 or 4-field capstan lock mode, we see the multiple vector dots are minimized or disappear. This is because SCH phase correction is taking place. Chroma phase shift. This portion shows full field color bar signal in playback mode. No chroma phase shift problem exists. When switched to E2E mode, showing SMPTE color bars, a chroma phase shift problem exists. This is caused by RV7, the decoder axis phase being misadjusted on the DEC42 board. This adjustment sets up the phase of the subcarrier used to decode the chroma signal into its R-Y, B-Y component. The key here is that the problem only exists in an E2E composite mode. Overmodulation. This is the symptom of overmodulation called bearding. This is most noticeable when looking at black to white transitions. This can be caused by several possibilities: worn or dirty video heads, worn tape, white clipping misadjusted while recording excessively hot video, high frequency circuits misadjusted, record current misadjusted. Overmodulation is caused when the sharp transitions are recorded and this signal is played back. The frequency of the playback signal changes from low to high and its level drops. If the zero cross point is lost due to this level drop, the demodulator cannot reproduce this signal correctly, and an inversion phenomena occurs in the RF signal, resulting in bearding. Note that the vertical shift is caused by recording this symptom while the defective machine is in a confidence mode. This is the mode that shows the strongest symptom of overmodulation. High-frequency streaking. This symptom shows white streaking, similar to the overmodulation symptom, except here you see white streaks instead of black streaks. This is a high-frequency problem caused by the demodulation process. In this case, specifically the high-frequency balance is misadjusted. RV15 on the DM56 board. This symptom is apparent in playback mode of a high-frequency signal. Poor frequency response. Now we see poor frequency response problems viewing a gated sweep signal in playback mode. First we see video and the waveform of a good frequency response. Note the flat response out to 4 MHz. The last frequency packet is 5 MHz. Next, we see a weak frequency response, observing the drop in the high-frequency portion of the waveform. This can be caused by worn video heads, worn tape, or frequency response problems with the modulator or demodulator circuits. White and green line at top of picture. This symptom is no more than the white reference pulse switch, located on the modulator board, being left turned on. This is used for adjustment purposes only. When we turn on S1, MD46 board, a white and green line is inserted into the vertical interval, noticeable at the top of the monitor in underscan mode. A rotary switch, also on the MD46 board, changes what line this is located on, limited to the first several lines at the top of the picture. Note, this white and green line will not be recorded on tape. Y dropout compensation. This video shows the symptoms of misadjusted or malfunctioning dropout compensation, DOC, circuit. First we see color bars with dropouts apparent. If the DOC is misadjusted, there is more distortion if playing back in a DT mode. You can see the picture breakup. The tracking-like problem is more prevalent when shuttling the tape in a DT variable mode, from reverse 1 times tape speed to forward 2 times tape speed. Notice that when in a stop mode, the guard band noise should just be covered up by the gray band when wide dropout compensation is adjusted properly. Also, viewing an oxide tape in DT variable modes should show no breakup in the picture. C dropout compensation. When the chroma DOC is misadjusted, the symptom will be horizontal lines of chroma going through the video where there is dropouts on the tape. We can see several dropouts and minor picture disturbance. Now we see more severe chroma DOC problems. This shows up as various chroma signal distortions, including chroma lockup problems. DT bidirects. Here we see a video level difference between play mode and DT variable mode when playing back a signal that was recorded from a composite source. You observe the correct level in play and then incorrect levels in DT variable. The signal level should be consistent between these modes. When the level is changed in a DT composite mode, check the DT bidirect circuit adjustment RV24 on the DM56 board. Carrier noise. As the subcarrier noise is increased, the white bar turns noticeably reddish or greenish. Carrier noise leak shows up as a carrier shift on the vector scope. We see this while carrier leak RV6 is being misadjusted on the encoder. The vertical axis shifts up or down on the vector scope, causing a slight change in hue and saturation. While this happens, we also see slight hue shifts to the color bar signal. Y DC level. The video output Y DC level adjustment can cause tearing or lockup problems to the video outputs 1, 2, and 3, and the monitor out if misadjusted too low. Note the effect as the pot, RV7, on the VO18 board is adjusted. A similar distortion will happen to video output 3 and monitor output only when RV14, character pedestal level, is misadjusted. Betacam SP main parts replacement. Head drum assembly. This first procedure demonstrates the removal and replacement of the head drum assembly. We begin by removing the brush assembly. The cleaning roller block, as you can see, has already been removed. Two connectors are disconnected from the SR26 board. These are CN661 and CN662. Now remove the plastic brush cover protector. The brush assembly is removed by using a 7mm socket driver. Now everything on the top of the drum is clear. The next step would be to remove the 4 connectors on the motherboard, MB116, located between the DEC 42 and DM56 boards. These 4 connectors are CN114, 115, 116, and 117. Also remove the retaining clip to loosen the wires so that they can be fed through the chassis. Two connectors will have to be removed from the RE28 board located underneath the machine. These are connectors 812 and 823. It takes some time to remove the harnesses through all the cable clamps and fold-down pins. Now remove the 2 connectors from each of the RP29 boards. To do this, the metal shields need to be removed. These connectors are CN101 and 102 from the RP29C board and CN1 and 2 from the RP29Y board. At this point, all harnesses from the drum assembly have been freed and the drum can be removed. 3 screws can now be removed from the underside of the chassis. The bottom panel and 2 SY boards have already been removed. It is best to put the unit on its side and remove the screws while holding on to the drum from the top side. This will prevent the drum from falling out or prevent stripping the screws. While the drum is being lifted out of the machine, the harnesses can be pulled out from under the threading ring. To install the new drum assembly, place the 6 wires back through the hole in the chassis as shown, and then take the 4 wires that go to the RP29 boards and pull them underneath the threading ring to the back of the mechanical chassis. Now lower the drum into the hole of the chassis. The drum can be secured to the chassis with the 3 fixing screws. The harnesses can now be rerouted to the appropriate boards, be reconnected, redressed, and reclamped into place. First, the 2 connectors to the RE28 board are reconnected, CN812, and then the big bundle, CN823. Then you see that the 4 wires are placed through the space in the sidewall of the chassis to be pulled through to the motherboard. These are the 4 connectors, CN114, 115, 116, and 117. These connectors are color-coded. Now install the brush assembly. Ensure that the brushes are making good contact with the slip ring. Secure the brush cover back into place. Finally, install the cleaning roller block and connect the 2 connectors on the SR26 board. The adjustment procedure would be the final step. For this, see Section 523 under Replacement of the Drum Assembly in the Service Manual. Replacement of the capstan motor. This first view shows the capstan with the threading ring intact. All three of the fixing screws can be reached with the threading ring remaining in the machine. Only the pinch solenoid block would have to be removed before you could remove the capstan. You must turn the machine on its side to get to the bottom of the mechanical chassis. Now you can remove the connector, CN1, from the capstan motor block. The three fixing screws are removed from this side. The capstan can now be pulled from the machine. Here is a close-up of the capstan. Notice the buildup of dirt or particles on the shaft. This shows why it is necessary to clean the capstan shaft periodically when you do a tape path cleaning. Here it shows the installation of the capstan. Reinstall the capstan from the bottom of the machine. Secure the three fixing screws from the top of the chassis and connect and redress the wire harness. For the adjustment procedure, see Section 523 under Replacement of the Capstan Motor in the Service Manual. Audio Timecode Head Assembly. The procedure described in Section 5 of the Service Manual is the replacement of the audio timecode head, which takes much more time to remove and replace than replacing the complete assembly. This is because it takes desoldering and soldering 6 wires and many adjustments to align an individual head. On this tape, we are removing the assembly as one complete unit. The advantage is that there is very little time spent installing and there is almost no alignments necessary. Now that the cleaning roller block is removed, the top of the audio block assembly can be reached. Remove the 2 fixing screws securing the holding plate. Remove the holding plate. The audio assembly can be lifted out. Of course, the harnesses would have to be freed from the wall of the chassis and unplugged from the motherboard MB117 before the unit can be totally removed. Here it shows a close-up of the audio assembly. On the left-hand side is the audio timecode erase heads, then the audio timecode record playback heads. Finally, the audio confidence heads. The confidence stack is the same as the RP stack, except the bottom head is not used. Replacement of the CTL head. This section of the tape demonstrates the replacement of the CTL head. Because there is little clearance between the CTL head and the head drum, there is no slack in the wires at the back of the CTL head. It is necessary then to make some slack in the wire to move the head away from the drum to unsolder the wires from the CTL head. The wire runs through the holding bracket as shown. The bracket is loosened and the wire is removed, giving us the slack necessary. There are two screws that need to be removed. They are the fixing screw and the step screw. Now we can pull the CTL head away from the base enough to unsolder the two wires. Note the position of the leads. Remove the CTL head. Here we see a close-up view of the CTL head. Note that there are two small screws that secure the CTL head to the adjusting plate. You would have to remove these two screws to replace the CTL head. To reinstall, the leads need to be resoldered to the head. The red wire goes to CX, and the white wire goes to CY. Redress the wires underneath the mechanical chassis by placing them back in the holding bracket. The CTL head is moved back into position and the fixing screw and step screw are tightened down. Once the CTL head is completely installed, the adjustments in Section 523 under replacement of the CTL head would need to be accomplished. Supply tension arm assembly. This procedure can be accomplished as described in Section 515 of the Service Manual, but the videotape demonstrates removing the complete tension arm assembly with the threading ring removed from the machine instead of just lifted up to gain access to the TR block. You may do this either way. By removing the threading ring, it gives you an opportunity to inspect the ring for wear and tear. If you don't want to remove the threading ring entirely, follow the steps 1 through 3 in the replacement procedures. Step number 4 has you remove the portion of the tension arm assembly that is shown in the illustration. It is recommended to replace the complete assembly. To do this, on the bottom side of the machine, carefully remove the connector of the tension arm assembly by placing a flat blade screwdriver on the bottom of the TR18 board and pulling the wires up. This prevents the fragile TR18 board from breaking. Now we can remove the two fixing screws that hold the tension arm assembly to the chassis. With the threading ring removed, the tension arm assembly can easily be lifted from the chassis. The shaft that the return arm assembly sits on has been known to bind. If that's the case, That return arm assembly needs to be removed. The shaft needs to be cleaned thoroughly and relubricated. The process of removing that shaft involves removing the E-clip on top and the two small screws holding the brass leaf spring underneath the S-tension regulator arm. Note that two small screws are held by locking compound. The locking compound needs to be loosened with heat before removing the screws to prevent the screws from being stripped. Now the tension arm assembly is shown being installed. After replacement, the adjustment procedures in Section 523 under replacement of the tension regulator block would have to be performed. Replacement of the threading ring. This section of the tape demonstrates the replacement of the threading ring. Remove the pinch retainer, the full erase head block, the pinch solenoid block, the ring sensor block, and the audio time code block. Turn the gearbox pulley until the pinch roller is located in front of the audio time code block assembly. Disconnect the two leads going to the brush assembly. Loosen the two screws of the gearbox and back the gearbox out of the way so it is no longer engaged with the threading ring. Finally, loosen the fixing screw of the ring roller located behind the drum and release the hold on the threading ring. Now, the threading ring can be removed from the machine. As it is pulled out from behind the drum, ensure it does not touch the heads or damage the surface of the drum. The threading ring is shown being installed now. Note that the reference for the position of the threading ring is that the pinch roller should be positioned in front of the audio assembly. As the ring is placed back in the machine, the T-drawer arm is moved out of the way, and the threading ring is positioned between the rollers that control the S tension regulator arm and the rollers that control the T-drawer arm. Check that the ring roller in the back is engaged in the threading ring properly. Reinstall the ring sensor, the pinch solenoid block, and the pinch retainer. The gearbox should be engaged after this is accomplished. Finally, complete the installation by installing the cleaning roller block. You would then proceed with the adjustments in Section 523 under Replacement of the Threading Ring.
purpose of the tracking adjustment is to provide standardization or interchangeability between Betacam VTRs. Thus, Betacam recordings can be played back on any Betacam playback unit with equal signal quality. The video head traces its path down the recorded video track. How well the video head traces this path is due to the linearity of the tape path. If the tape path is non-linear, the video head will drift off track, resulting in a loss of the playback signal. This, of course, causes a disturbance in the picture monitor. This effect can be compensated to some extent with the front panel tracking control. However, performing the tracking adjustment with a standardized alignment tape on each playback transport in your facility will assure that these constant readjustments will be kept to a minimum. There are many elements that derive this tape path. One element is the tape path created by a narrow shelf of metal that extends around the scanner and forms the helical angle. This rabbit guide or lead line guides the lower edge of tape and controls the linearity for most of the track. It is important for this guide to be kept very clean. Distortions or uneven wear could cause an RF envelope display such as this. The other factors involved are the entrance and exit guides that control the linearity at the beginning and end of the video track. The Betacam transport employs 3 guides for the entrance: tape guide 1, tape guide 2, and the tension regulator. Tape guide 3 and tape guide 4 are used to control the exit and are placed on opposite sides of the audio block. On the entrance side, the upper edge of tape is controlled by the upper flanges of the tension regulator and tape guide 2. Tape guide 1 and the rabbit guide control the lower edge of the tape. And so the tape is fed accurately to the scanner. On the exit side, the upper edge is controlled by tape guide 3 and tape guide 4 controls the lower. The tape then continues past the capstan and returns to the take-up reel. The first step of the tracking procedure is to check the tension of the tape path. The playback transport specification is 45 grams at the entrance of the scanner. This specification can be measured with a tensionometer or a tension scale. The tension regulator operating position and forward back tension adjustments should be performed to meet the specification. In addition, the tension should be equal at the upper and lower edges of tape around the rest of the threading ring. This is specified by the tape run adjustment procedure listed in your manual. In step 2, the entrance linearity will be adjusted by monitoring the off-tape video signal while playing back a Sony Betacam alignment tape. The test point to be measured is listed in the tracking procedure. Each guide is adjusted in turn, starting with the tension regulator, then tape guide 2, and finally, tape guide 1. Since a tension regulator is to be adjusted first, it is important that tape guide 1 and tape guide 2 do not influence the tape path. Clearances are made where the flanges of tape guide 1 and tape guide 2 contact the tape's edges by turning the adjusting nut at the top of the guide. The tension regulator's height now determines the entrance waveform. It should be adjusted so the waveform is flat at the entrance side. If an error exists, pressing down or pushing up on the tape will indicate whether to raise or lower this guide. In addition, slightly turning the tracking control of the VTR will decrease the waveform and magnify the error. Because the tension regulator controls the upper edge, you must make sure the tape contacts the upper flange of this guide. This is controlled by the slantness adjustment of the tension regulator. In addition, the tape tension at the upper and lower edge should be equal. This is also controlled by the slantness adjustment. Tape guide 2 is adjusted next. Since this guide also controls the upper edge, you must assure contact at the upper flange by raising the tension regulator slightly from the last adjustment. This causes a slight distortion in the waveform. Tape guide 2 will correct this error by forcing down the tape path. Adjust the flange of tape guide 2 so that the waveform is flat. Check that there is no curl at the flange of tape guide 2. Tape guide 1 is used to control the lower edge of tape. Since the tape path is now stable at the upper edge, tape guide 1 is adjusted so that it contacts the lower edge of tape without tape curl. Each guide should be locked in place by the set screw at the top of each guide. Check for any distortions by turning the tracking knob back and forth slightly on the VTR. The envelope should remain flat. In step 3, the linearity of the exit side is adjusted. This procedure is very similar to that used for the entrance side. Tape guide 3 controls the upper edge and tape guide 4 controls the lower. Tape guide 3 should have a clearance at the upper flange and tape guide 4 should be adjusted so that there is a slight nonlinearity on the exit side. Tape guide 3 is then adjusted to correct this nonlinearity and make the envelope flat. In addition, the leading guide roller on the threading ring should be adjusted so that the tape contacts the upper flange. As a final check, the tracking knob should be turned slightly back and forth and the waveform should remain flat. In addition, all guides should be locked down and checked for tape curl. If this procedure does not work for a BVW-40, don't call me, I'll call you. This is Sony Broadcast, over and out.
digital video.